Hi, this is Professor Fernandez, and this is video 3 in lesson 23. We're talking here about transcendental functions and infinite limits involving them. So there are 3 examples here on the screen from Calculus Simplified that we are going to go through. Let's jump right in here. Oh, I should mention one thing. On the right here, if you want a quick review of limits involving infinity, either going to infinity or, as we'll see here, yielding infinity, so take a look at the videos in lesson 7. So that will give you a review of those topics. Okay, so then let's jump into the first example on the left here. So this one says, evaluate the limit as x goes to infinity of ln of 1 plus 1 over x. Same sort of thinking here with limits, right? We want to try to think about whether the function is a continuous function. If it is, then we can draw on some results that we have learned earlier in the course about limits and limit laws and theorems. In this case, indeed, so 1 plus 1 over x, that has x down there, so at x equals 0, it's not going to be defined, won't be continuous there, but we are far away from 0, right? We're taking the limit as x goes to infinity. So for all non-zero x and really positive x, or I should say all non-zero x, and all other values that make it such that this is positive, then this composite function is continuous. Why am I requiring this to be positive? Well, remember ln of x, the domain here is x positive. So we want to make sure that this entire thing, whatever values it outputs, stay positive, so that indeed, so that ln of x is indeed defined. Okay, so I'm taking the limit as x goes to infinity then. I'm far away from the point where this is discontinuous. I'm well within the domain as x gets larger. I'm just taking the reciprocal of that number and then adding 1 and then taking the natural log. So that's still going to be a definite number. So I can pull in all the results that I have learned earlier in the course, which one of them in particular is sliding the limit inside the argument of the log. So I can write this limit as this first simplification. And then we're back to taking the limit of a function that looks like this. So we can analyze each piece separately. If I graph the function y equals 1, and I ask, to what value does it tend to as x goes to infinity? The answer is 1, because it's a constant function. If I ask the same question for 1 over x, though, this is one of the kind of fundamental limits that we talked about earlier when we first met the limits as x goes to infinity of powers of 1 over x. And we have 1 divided by a large number, and this tends to 0. Right? Think about 1 over 10, 1 over 100. So this is 0.1, this is 0.01. So as the denominator gets bigger, the outcome gets smaller and closer to 0. So we are going then to use this fact again here to tell us that this limit is 0. And then we're left calculating ln of 1 plus 0. That's just ln of 1. Remember that ln of 1 is 0. That's one of the fundamental values for the log function. Okay, so we've arrived at the answer for the limit. Again, using some of the properties that we have studied earlier about limits. So I'm going to scroll down here and look at the second example. So what about limit as x goes to infinity of e to the minus x? There are a few ways that you could do this. First of all, you could look at this e to the minus x as a composite function and apply the same reasoning that I just did for the earlier example. Or you could also say limit as x goes to infinity, x, e to the minus x. You could use the fact that e to the minus x is 1 over e to the x, right? And then think about this as this function, this quotient of 1 and e to the x. So again, 1 doesn't go anywhere as x goes to infinity. It remains 1. And then down here, this is another fundamental limit. E to the x is an exponential function, kind of the prototypical one. So as x goes to infinity, the y values just keep getting bigger and bigger and bigger. They go off to infinity. So I don't like writing this, but it's useful intuitively. This is going to tend to 1 over infinity, which is 0. In other words, the denominator is growing very, very, very large and actually very fast, exponentially fast. And we're taking 1 and dividing it by that very, very fast growing number. So similar thing to what's happening up here. We get a very small number and it tends towards 0. So that's our limit. And then on the right hand side here, calculate these three limits. Notice that these are all involving trig functions. So we're shifting gears a little bit away from the exponentials and logs. And then what are we doing here? Notice that these are one-sided limits. Okay, so let's start with the first one, tangent x. So remember that this is sine over cosine, and that's the first thing that we want to recall because that is going to help us narrow down what's really going on with the pi over 2 here specifically. Okay, so how do I calculate this limit? Well, so if I look at the denominator here, I know that at pi over 2, cosine of pi over 2 is 0. So I would be dividing by 0 if I just substituted in pi over 2 for x. So I can't do that. However, I'm asked for the limit as x approaches pi over 2 from the left. So I do have some information about what type of infinity I'm going to get. And I should say that, how do I know that I'm going to get an infinity? Well, at pi over 2, sine of pi over 2 is 1. And cosine of pi over 2 is 0. So, at pi over 2, the y values are tending to 1 over 0, which is some form of infinity. What I mean by some form is I don't know if it's tending toward positive infinity or negative infinity, right? The left-hand limit here is going to help me figure that out. Okay, so cosine of pi over 2 from the left, right? What if I think of substituting in values very, very close to pi over 2, but slightly less than it? That's what I mean by cosine of pi over 2 from the left. Would give me something very, very close to 0, but positive. Okay, how do I know that? Well, let's think about the graph here. So this is x and this is y. And I'm going to plot here y equals cosine of x. So at 0, cosine of 0 is 1. Okay, and then at pi over 2, cosine of pi over 2 is 0. And then at pi, cosine of pi is negative 1. So remember, the graph of cosine goes like this, and then it keeps going that way and keeps going this way. So the thing to know is that pi over 2 to the left is like right somewhere like over here, just to the left of pi over 2. And you can see that as I approach pi over 2 from the left, I start off positive, 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 and I'm always positive, and then I get very, very close, and then at pi over 2 I'm 0. And then if I keep going, certainly pi over 2 from the right, I get negative values. So this again substantiates this claim that if I look at values close to pi over 2 but slightly less than it, the cosine of it is very, very close to 0 but positive. So then I can say, oh, so sine of pi over 2, let me erase this arrow to not confuse anyone, sine of pi over 2 from the right, I don't really care in this sense because I'm going to get either 1 from the right or from the left. But we could draw the sine graph in a minute. But I'm emphasizing here that the denominator, oops, I should have said sine of pi over 2 from the left. The denominator, what we just analyzed, is 0 from the right. Okay, so up here you have a number that's very, very close to 1. We could talk about whether it's slightly less than 1 or slightly bigger than 1. It doesn't matter, because in the denominator we have a number that's very, very close to 0 and it's positive. So we're dividing these two, and therefore that is going to give us a tending toward positive infinity. Again, because this is going to be a positive number, that's going to be a positive number. So in the convention that we have been using in this class, I'm going to write does not exist, right? This limit does not tend to a specific number, but we do have information about where it ends up. I shouldn't say ends up to confuse anyone, where it tends to, right? It tends to positive infinity. The y values are getting larger and larger and positive. Okay, so that's the first limit, and I've taken it slow and done a lot of work, in part because now I want to speed it up with these next couple of limits. So what do I do then for this one? Well, this one is going to pi over 2 from the right. So very similar type of analysis. What if I look at pi over 2 from the right, and I look at tangent? What's going to happen? Well, I just erased the graph, but remember that cosine of pi over 2 from the right, as I approach pi over 2 from the right, I tend to 0, but now I tend to 0 from the negative numbers, right? Remember the graph here was pi over 2 and cosine was doing this. right? So if I approach pi over 2 from the right, then the y values are negative, negative, negative as I approach y value of 0. Okay, so I have a very small number in the denominator that's negative. In the numerator, I have 1 that could be slightly below 1 or slightly above 1, doesn't matter in this case. I'm getting 1 over 0 that tells me it's infinite, but now I'm dividing this positive number by this negative number. So I get a negative number. So my answer for this one is going to be, again, does not exist, but more information, it tends to negative infinity. Great. And then one last one to do, part C over here. What about 1 over sine x? So let's take a look at that one. 1 over sine x. So this is cosecant x, and we could draw the graph for cosecant x, or we could reason again as we just did. So sine of 0 is 0, so I can't write down any limit information if I were trying to do this using continuity, because the function is not continuous at x equals 0. But I could get some information, right? So what if I approach 0 from the right? Okay, so now let's go back and draw a graph of sine. So sine looks something like this. And this is 1, and this is minus 1. This is x, and this is y equals sine x. So if I approach 0 from the right, here is x equals 0, and I'm approaching 0 from the right, from numbers above 0. You notice that all the y values are positive, and they're decreasing towards 0. So 0 from the right, as I take the sign of it, gives me something that is tending to 0, but approaching from the positive side of 0. So this tells me all the information I need to know here, right? So I have 1 over 0 from the right. That's going to tell me that the limit, in this case, to put it back up here again, does not exist, does not tend to a specific number. However, I have that information that it tends toward a positive infinity as the result for this. Okay, so I've gotten my 3 limits here, so that sounds good. So that finishes this example. A couple of things that I want to mention. If I scroll back or zoom back out here, in the infinite limit case, on the left-hand side here, I took the limit as x goes to infinity, and I got a number. So remember, that tells me that y equals this number is a horizontal asymptote of this function. So that's another cool thing about limits. They enable you to actually calculate the horizontal asymptotes of functions. A similar thing happened over here. Took a limit as x goes to infinity of this function, and I got a number. So y equals this number is, again, the horizontal asymptote for e to the minus x. Great. Similar thing happens on the right-hand side. So if I take the limit as x approaches a number, and I get some form of infinity, function just goes off to larger and larger y values, or smaller and smaller y values, tending toward infinity or negative infinity. Those are vertical asymptotes. So I can say that x equals, oops, let me not use that highlighter marker. X equals pi over 2 is a vertical asymptote of tangent of x. This limit right here is all that I need. If the limit approaches positive infinity or negative infinity, either one of those is sufficient to tell you there's a vertical asymptote. But in this case, we did it both sides, right? So not only did we approach from the left, get positive infinity, we approach from the right, got negative infinity. So this is, double confirmation, if you will, that we have a vertical asymptote here. Okay, and it doesn't matter, by the way, that one side is approaching positive infinity, one is approaching negative infinity. Okay, and then the last one, same thing with this last calculation here. As x goes to 0 from the right, again, we're going off to infinity, so that tells us that there is another vertical asymptote for the function 1 over sine x, otherwise known as cosecant x. Great, so I'll zoom out and mention one last thing here. This is basically the last video in which we are doing limits of transcendental functions. In the previous 2 videos, 23.1 and 23.2, the first one we looked at some of the basic limits where we could use continuity. The second one we looked at some tricky trig limits where we had to use multiplication by conjugates, and we had to group things in specific ways and maybe use some substitution. And then in this video, of course, we looked at infinite limits. So at this point, throughout these 3 videos, if we add this here now, we have talked about everything we've learned about limits in the context of transcendental functions. So I highly encourage you to go ahead and go back to these videos and those ones that I've been mentioning, the videos in lesson 5, 6, and 7, because that's really all the limit content in terms of the videos across all the families of functions that we've now studied in calculus. All the algebraic functions, but then also everything across these videos, the transcendental ones. Great, thanks for watching.